Hello and welcome friend once again. In this video we discuss about first fundamental theorem of integral calculus. The statement of the first fundamental theorem of integral calculus is on your screen. You can see that it consists of two parts. If we have a bounded and integrable function on closed interval a comma b, then we can define a function capital F of x as an integration of f, and this function is continuous function. And if f is a continuous on closed interval a comma b, then the defined function capital F is derivable on close interval a comma b, and derivative of that function f dash of c equal to f of c. So here we have defined in this theorem a relation between derivative and integration. As we know that derivative integration is nothing but an antiderivative, and these are the inverse operator, but here we are going to prove how they are inverse operators. So first we consider here what is a given. F is a bounded and integrable function. F is bounded. Let us see the proof of this theorem. F is bounded. We consider first F is bounded on close interval a comma b. That means all the values of this function f of x lies between capital K, where K is a number, real number, for all x belongs to close interval a comma b. Function is bounded, therefore there exists a real number K such that mod of f of x is less than equal to K. Now what is a given? It is a given. Let us consider, let we have 2 points x1 and x2 belongs to the closed interval a comma b, such that this a is less than equal to x1 and x1 is less than x2, and which is less than equal to b. We choose these 2 points. Let us calculate f of x1. F of x1 is equal to integration a to x1 f of t into dt, and f of x2, capital F of x2, equal to integration a to x2 f of t into dt. Then capital F of x1 x2 minus f of x1 equal to integration a to x2 f of x1 f of t into dt minus integration a to x1 f of t into dt. So this is the points where we are integrating. Here is a x1 and x2. From this whole part a to x2 we are subtracting a to x1, these parts. So the range then terminates from the x1 to x2 points. Therefore this value capital F of x2 minus capital F of x1, this will be integration x1 to x2 into f of t into. So friends, if we take the modulus value of this term f of x2 minus f of x1, then this modulus value is equal to mod of integration of x1 to x2 f of t into dt, mod of this. Again this modulus value is less than integration a x1 to x2 mod of f of t into dt, but mod of f of t is less than equal to k. Therefore we have this mod of f of x2 minus f of x1 is less than k into integration of mod of x1 to x2 dt. But integration x1 to x2 dt is t. This is equal to k into t from x1 to x2. Okay, x2 is greater than x1, so this is k into x2 minus x1. We get this f of x2 minus f of x1 is a less than k into x2 minus x1. Now this value f of x2 minus x1 is less than epsilon whenever this value mod of f of x2 minus f of x1, this will be less than epsilon if the greater value k into this mod of x2 minus x1 will be less than epsilon. That is, mod of x2 minus x1 is less than epsilon divided by k. Let us take this as a delta. Then what we get here, x1 and x2, these are the any two points of the closed interval a comma b, and mod of f of x2 minus f of x1 is less than epsilon. For epsilon greater than 0, there exists delta greater than 0 having the value epsilon divided by k, such that whenever if x2 minus x1 is less than delta. What is this? This is nothing but a definition of uniform continuity. Uniform continuity. That means this function capital F is uniformly continuous. And there is one theorem between the uniform continuity and continuity, relation between uniform continuity and continuity. That theorem is every uniformly continuous function is a continuous, and this shows that capital F is a continuous function. Capital F is continuous on closed interval a comma b. So what we have shown that? We have shown that if f is a bounded and integrable, then the function capital F, which is defined as the integration of f between the limit a to x, is continuous. Now we prove the second part. If small f is a continuous, then the derivative of this function capital F is nothing but small f of c. Now we move to the second part of this in theorem. The second part of this theorem, if f is continuous at point c of closed interval a comma b, so f is continuous at c, where c lies between a and b. There, that means, that is, for epsilon greater than 0, there exists delta greater than 0, such that mod of f of x minus f of c is less than epsilon whenever mod of x minus c is less than delta. For which values of x this condition is satisfied? C minus delta is less than x less than c plus delta. Okay, but we choose now 2 points such that c minus delta is less than less than equal to c less than equal to t less than c plus delta. We have taken these 2 points s and t between this interval, between these 2 points c minus delta and c plus delta. Then f of t minus f of s divided by t minus s equal to 1 divided by t minus s into f of t. F of what is f of t? A to t f of x into dx, and f of s a to s f of x into dx. This is equal to 1 divided by t minus s integration s to t f of x into dx, and 1 divided by t minus s into integration s to t f of c into dx equal to f of c is a constant 1 divided by t minus s. Integration of dx is x between the limit s to t equal to f of c into 1 divided by t minus s into t minus s. T minus s, t minus s will get cancelled and we have f of c. So let us put this value here. Function is a continuous, therefore we put, let us calculate now. We calculate the term mod of f of t minus f of s divided by t minus s minus f of c equal to, what is the first term? The first term is now t minus s integration s to t f of x into dx, and f of c 1 divided by t minus s integration s to t f of c into dx. Okay, now see the terms which we can take common terms, and out of this modulus value here t is greater than s and t minus s is a positive, therefore we write it as 1 divided by t minus s into mod of integration. We can take integration common, integration s to t, and f of x here minus f of c into dx. Okay, but we know that from the definition theorem of modulus, we have 1 divided by t minus s integration s to t mod of f of x minus f of c into dx. But mod of f of x minus f of c is less than epsilon, so put greater value 1 divided by t minus s integration s to t epsilon into dx. 1 divided by t minus s, epsilon is constant and integration of dx is x between the limit s to t equal to epsilon into 1 divided by t minus s into t minus s. T minus s, t minus s cancel and we get that 1 divided f of t minus f of s divided by t minus s into minus f of c is less than epsilon. Okay, but we know that f dash of c equal to, what is f dash of c? Capital F dash of c is nothing but this, this is the limit of f of t minus f of s divided by t minus s as t tends to s. Okay, so this is the definition. Since we have taken this point s and t near to c. Okay, so this is nothing but f dash of c, and this shows that in the limiting case this value f dash of c equal to f of c. So derivative of the function is f of c. This function which we have defined f of x, what is the definition, is integration a to x f of t into dt, is called as a primitive of f, primitive of small f.